Hi guys, welcome to our first video in Baby Chem Bootcamp. The point of this video is to help you review and remember what you learned during Chemistry 1. Maybe that was a year ago, maybe it was 2 years ago, but I want to make sure that you have a good foundation before you go into AP Chemistry and learn much more in-depth chemistry. So this video correlates with Unit 1 in the Brown-LeMay textbook. Even if you don't have the textbook with you, that's okay. You don't need it to watch this video. But when you do have the textbook, it's good to know that Unit 1 goes with this video. I have also provided you with an outline so that you don't feel like you need to write down every single thing that's on the slide or that I say, and that you have that as an additional resource. Let's take a look. So we have to start with the beginning, right? Chemistry is about the study of atoms and how they combine together to create everything, right? Everything is made out of matter, and matter are things that occupy space and have mass. That is just the basics of chemistry right there. Everything else that we talk about chemistry is extrapolating on the idea of matter. And atoms are the building blocks of that matter. And we know that the periodic table is our giant mnemonic device for remembering how all these beautiful elements relate to each other, and therefore how we can use them to make different bonds, different compounds, molecules, mixtures, and all the fabulous things around us. By the way, at any point during a video, if you need to read the slide more, you can always pause me and take down those notes. All right, we classify matter into 3 different states, going all the way back to elementary school here. And we know that this is a solid, a liquid, and a gas. We will be spending whole units on these different phases of matter and how to measure them and how to figure out how they're going to behave and interact. You should remember in Chem 1 a whole unit on gas law. Definitely will be spending more time on that. And a little bit in Chem 1 about kinetic energy and heat of fusion and heat of vaporization, and we'll be spending more time on that also. So something that tends to confuse Chem 1 students and some adults is pure substances versus mixtures. And I love this graphic because it breaks down really nice and easy for us. Here up at the top we have all our matter, and all matter can be divided into 2 different categories of either being a pure substance, which means that everything in that substance is the same, or it is a mixture, which means that you have 2 or more substances being brought together to make up that matter. And so hopefully we remember from, I'm going to get my pen here, from Chem 1, of course, elements are pure substances, and we know our elements from the periodic table. Love the periodic table. We will talk about it a lot. A compound is going to be 2 or more atoms that are bonded together, but within our substance they are all the same. So here we see this actually looks like carbon dioxide hanging out here. So here we see our compound, even though we have a compound of carbon dioxide, our substance is only made out of that one compound. But when we get into mixtures, we have two different compounds hanging out together. They're not bonded together. So remember, to make a compound, we have things that are bonded together. And when we have a mixture, we have different things that are not bonded together. So the big difference between these two is the word bonded or bonds. So compounds, they're bonded. Mixtures, they are not bonded. So yes, bonded, not bonded. Go this way, not bonded. Go that way, yes, bonded. So here we see we have a homogeneous mixture. That means that everything is blended together and you can't tell the difference between the compounds that are hanging out together. And actually here it looks like we have a pure element, and here we have a diatom. And we'll talk more about diatoms in just a minute. So maybe here we have a helium atom, and here we have hydrogen. Hydrogen's a diatom, so helium and hydrogen hanging out. And they're going to be homogeneous. They're going to be mixing all together. A heterogeneous mixture means that we have two different substances that do not want to mix together. The one that can pop into our heads really quickly, even from childhood, is oil and water, right? Oil is a pure substance. Pure distilled water is a pure substance. We know water coming out of the tap is not necessarily a pure substance, right? There can be other things in it. But if we have distilled water and oil, those are two pure substances. Bring them together. We have a mixture, but it's going to be heterogeneous. They are not going to mix together, and we're going to have an interface, right? We're going to have these layers. And here, it actually looks like we have carbon dioxide and water at an interface here. So this is a gas. We can see they're showing, you know, movement there with that kind of like streaky look in the graphic. And then here we have a liquid, or even how close these are, it could be a solid. So this could be ice, right? And carbon dioxide. So hopefully we remember that from Chem 1. Let's go to our next slide. Okay, just some vocabulary there for our mixtures. All right, properties of matter. So we have physical properties and we have chemical properties. Basically, physical properties is we can observe something without changing it. So, you know, if I pick up a piece of paper, right, I can look at it and I can say, I can weigh it, I can measure the length of it, I can see that it's white, I can smell it, right, all these kind of things. It's still a piece of paper. I can even cut or rip the paper into smaller pieces. It's still a piece of paper. These are all physical properties. Ripping it is a physical change. Chemical properties would be me taking this piece of paper and putting acid on it to see if acid would burn through it, or putting solid iodine on it to see how the paper reacted with iodine. I'm not going to have usable paper after that. So those are chemical changes and chemical observations. When we look at chemical properties, we have to actually conduct an experiment on the substance to see how it behaves. And so we no longer have that substance after that. So a really fast example of that is if I take this piece of paper and I burn it, I am no longer going to have a piece of paper that I can use. I tend to look for the action words for chemical change. React, burn, rust. These are words that signal to us right away that we have a chemical change and we're making observations about chemical properties of the substance. Do not get confused with freezing, melting, boiling, condensating, sublimating. These guys, those changes in physical states or states of matter are physical changes, and those temperature points in which those changes occur are physical properties of the substances. On the other hand, burning something is a chemical change. Intensive properties do not depend on the amount of substance there. Extensive properties do depend on the amount of substance there. So intensive properties would be like the paper is white, the paper burns, the paper can be dissolved with acid, right? These are intensive properties. Extensive properties would be the length of the paper, right? If I rip the paper in half and I have a different size, that length is an extensive property. If I weight is an extensive property, right? If I have more paper, if I have a whole stack of paper, or if I have card stock that's very thick, that is changing the amount that I have changes that extensive property of mass. So intensive property, no matter how much you have of the substance, that data, that observation, those properties are not going to change. And extensive properties, how much I have of the substance is going to change that property. Separation of mixtures. We do quite a bit of this in Chem 1. We will be using these methods in labs that we do all year long, but we're not going to actually talk about these methods themselves. This is one of those things you need to remember how to use it so that you can have it as a tool in your toolbox when we go to do labs in AP Chemistry. So chromatography, remember that is using filter paper to separate out pigments or liquids based on their molecular size. So larger molecules are going to move slower and smaller molecules are going to move faster. The lab that you did back in Chem 1 or maybe even elementary school was you had a piece of filter paper, and I'm going to use yellow, and you put, that's not very dark, is it? Let's see if we can get a better color. Okay, and no, that's not a better color. No. All right, let's try this yellow. There we go. And you got a marker and you put a little band of color, and then you put the filter paper into a beaker that had just a little bit of water in it, or maybe it had an alcohol, and the color went up the paper and separated out depending on its size. So the larger molecules move slower, and they're not going to move as quickly as the water or alcohol, depending on what you're using, moves up the filter paper. It grabs that pigment and pulls it up the filter paper, larger molecules are going to stay lower, smaller molecules are going to move faster. Filtration, we actually have a couple of different ways that we can do filtration. We can filter solids out, right, using different size meshes or sieves or filters. Like think about in your furnace or your air conditioning unit in your home and in cars, there are filters so that as the air goes through them, the filter grabs things that you don't want to keep breathing in. So like pollen, if you have a pet, it could be cat or dog hair, those filters are going to grab those substances. Well, if you think about like cat and dog hair, those are pretty big. So you could grab cat and dog hair with a filter that has pretty large holes. So, you know, if I had a filter, like a piece of mesh that had holes this big, that would grab that cat and dog hair, right? But let's say I want to grab pollen. Pollen's going to go right through this, right? So we're going to want a smaller mesh like this, right? And let's say I want a filter that's going to grab bacteria out of the air. Then I'm going to want an even finer mesh. I can't turn that. Okay, and we can do this with particulate matter, like solids. We can also filter out liquids. Liquids, actually, the molecules have different sizes. So a very viscous liquid, like an oil that's very thick, is not going to need as fine of a filter as something that is very thin, like an alcohol or something like that. All right, distillation and evaporation. Evaporation is where we use heat to evaporate off or remove a liquid. Now we can do this in two different ways, and you will do this in AP chemistry. So evaporation is where we have a solid that has been dissolved in a liquid, and we evaporate off the liquid and we leave behind the solid. The lab that you most likely did in Chem 1 was you had salt water and you heated that and evaporated off the water, and the salt was left behind in your evaporating dish. We know salt water is a homogeneous mixture that we have out in the oceans, right? In seawater. And if we take some seawater and we boil it, the water is going to evaporate off and the salt will be left behind. Distillation is basically evaporation, but our mixture is made out of two liquids or more. We can have more than two liquids, but let's say just two liquids. And they have different evaporation or boiling points. So if you have two liquids, so we would use a round bottom flask. Oh, that's a bad drawing. That's okay. And we have our Bunsen burner here. So I use this little digital tablet thing, and not the easiest thing to draw with, as you can see here. And so in our flask, we have a liquid. Now, if we know that our flame is going to heat to, let's say, 800 degrees Celsius, and we know that in here we have two liquids, one that boils at 900 degrees Celsius, I'm just going to keep my numbers easy for the example here, and one that boils at 700 degrees Celsius, then when we get this flame going, the 700 degree Celsius substance is going to boil off. I'm going to use a different color there. So the 700 degree one is going to start to leave, and the 900 degree one, we'll keep that one yellow, is going to stay behind. So our 900 degree one is going to stay here. So we have evaporated off the mixture with a lower boiling point, and we will be doing this in AP Chemistry. Now we do have a way of collecting this vapor and recondensating it so that we can collect that liquid into a different beaker, and we will talk about that during the year. Fractional crystallization is taking a liquid and turning it into a solid, and then separating those two solids. We do have other separations of mixtures, like we can use magnetism if we have two things that are combined, one's magnetic and one's not. We can also dissolve things, right? So fractional crystallization is a good way to do that too, is if we have two solids together, we will add a liquid that will dissolve one of them and not the other one. Then we can separate off the solid from that liquid, and then we can then evaporate off the liquid of that other solid. And then we've separated those two solids. So lots of different ways we can use these separation techniques in conjunction with each other. And we will do more of that in class. All right, units of measurement. I'm not going to read this to you guys, but this is our basics that we use in chemistry. No, the big one I will point out is note that it's Kelvin and not Celsius. When we're doing quick examples here, it's okay for us to say Celsius, or when we're in the lab, we might use Celsius, but when we go to do our calculations, temperature is in Kelvin. And does everyone remember what we use to convert Celsius to Kelvin? 273. Good job, guys. I knew you'd remember. All right. This one, need to learn it. Most of it you know. You guys know that a centimeter, right, is 100 centimeters in 1 meter, and a decimeter, and so on. A millimeter is 1,000. So just make sure that you guys can go back and forth using these prefixes along with the metric system. Notice the scientific notation here, right? So when we have a positive number in our scientific notation, that means that our decimal point is going to go to the right. So let's do an example. If we have 1.2 times 10 to the 2, that means that we really have 120, right? That 2 right there means that we moved the decimal place 2 places, so we have 120. If we had 1.2 times 10 to the negative 2, then we're going to move that decimal place to the left and get a smaller number. So we take that decimal place that's right there and we go 1, 2. So really what we have is 0.012. Okay, so that's our scientific notation there. If it's positive, our number is going to get bigger and the decimal goes to the right. If it's a negative exponent, then our decimal is going to move to the left and our number is going to get smaller. Back to our prefixes, note that when it has an A ending, it's going to get bigger. It's a positive exponent. And when we have an I or O ending, so I or O ending, that our numbers, our exponents are negative and our numbers get smaller. Our only one that's an exception is kilo. But that's a pretty good rule of thumb there. Ones that we'll use a lot: kilo, deci, centi, milli, micro, nano, pico. Those are the ones that we'll use a lot. And notice that we use the ones that take our numbers smaller compared to bigger, because in chemistry we're dealing with little teeny tiny atoms, right? So we tend to work with things that are smaller. Physics, on the other hand, you tend to use mega and giga and tera. All right, conversions. Oh, there's Kelvin again. We're going to do some conversion problems together. You know, it's really following the units. Make sure that you can do conversions using scientific notation, meaning those exponents, and can go from those different units back and forth. So these are all equivalents. A non-common or a non-SI common unit are our volumetric units. If you go back here, notice we don't have volume as part of our SI units, but volume is really important in chemistry. And so we are going to use milliliters and liters for our liquid volumes. We're going to use centimeters cubed and decimeters cubed for our solid volumes. Keep in mind that 1 liter equals 1 decimeter cubed. 1 milliliter equals 1 centimeter cubed, which is the same as 1 cc. For those of you who are thinking pre-med or want to go into medicine, syringes tend to be in units of cc, and that's just 1 centimeter cubed, which is the same as 1 milliliter. Density. Why is density, oops, didn't mean to do that. Why is density so important in chemistry? Well, remember, the definition of matter is things that take up space and have mass. That's density. So density is really important in chemistry. Something else that's interesting about density is that mass and volume are extensive properties, which means that they are affected by the amount that's there, right? If I have, you know, my water here, it's actually iced tea. If I have my iced tea, right? If I have this full of iced tea, this is going to weigh more. It's going to have more mass. If I drink all of this, it's going to have less mass. The amount that's there affects its extensive property. And then volume, right? If I have a teeny tiny square of gold, pick something fun, all right? Or if I have a big square block of gold, those are extensive properties. But when we put mass and volume together, those extensive properties cancel each other out, and density itself is an intensive property. Because as you increase mass, you increase volume. And as you increase volume, you increase mass, right? So those extensive properties of mass and volume cancel each other out. And hopefully we remember that our formula is density equals mass divided by volume. And our units are usually grams per centimeters cubed or grams per milliliter. All right, when we measure things, we're going to have a certain amount of uncertainty. Exact numbers are values that we know are absolutely exact, right? So if I take my pencil pouch and I count out all my, gotta have a Sharpie, right? And I count out all my pens and pencils, I will have an exact number of the pens and pencils that are in my pencil pouch, right? That's an exact number. If I count my number of students attending in class that day, that's an exact number. However, some numbers are not exact. They are inexact, and that's usually through a piece of equipment measuring something. So, a great example is I take my pencil pouch and I go over and I put it on one of the balances in the classroom and I weigh it and it says 2.31 grams. I write that down. Well, that has to be true because the balance told me so, right? It has to be accurate. But then you take my pencil pouch, same pencil pouch, we didn't do anything different with it, and you walk over and put it on a different balance in the room, and you get 2.2 grams. All right. Who's wrong? Who's right? We don't know. That's an inexact number. You can tell I'm outside, right? Hear the sirens. All right. Precision and accuracy. A dartboard is the best way to talk about this. You know, when you throw darts, you want your darts to go to the center of the dartboard. If you actually throw a dart and get it into the center, the bullseye, then you are accurate. And if you throw all your darts and you don't hit the bullseye, but all of your darts are clumped together in one spot, then you are very precise. So data can have two different evaluations there. Data can be accurate in that it is close to the known value that you should have. And it can also be precise, meaning that all your data is close to each other. So very often we will do labs with unknowns, and we will get a value for our unknown, and we'll have to look it up against a chart of known values to see what our unknown was. And there will often be a % error because of the inexact value of our equipment in the classroom. It would never be human error, right? We would never make a mistake during labs. Okay, sig figs. We're going to use sig figs a lot in AP chemistry because when you go out into academia or into the workforce and you are actually using your chemistry in a job or publication or research, you need to have significant figures. So, reminder that the big thing is to watch your zeros, right? Are they placeholders or are they telling you that you're very sure of something? So when we have zeros to the left of whole numbers, these are placeholders. So they're not significant. They're just telling us the value of those other numbers. So this particular number has 1, 2, 3 sig figs. Now this guy right here has 5 sig figs because these zeros after the decimal are saying, yeah, we're that sure. We really know that our equipment or whatever it is we're using to measure this is that accurate. And if we have no decimal point, then only zeros that are between whole numbers count. So for this guy, only this zero right there counts. So we have 1, 2, 3 sig figs. This zero is just a placeholder. He's not accurate. But these zeros are in between whole numbers. So all of these count as sig figs. And we have 5 sig figs. When we go to do math with our data, which we will do a lot of math with our data, there's 2 rules of thumb. If you're doing multiplication and division, then you go with the number of sig figs. So here we have, right, 1, 2, 3 sig figs. And here we have 1, 2 sig figs. So when we actually get our answer, we get 4 sig figs. Well, 4 sig figs is more accurate than our data. We can't have an answer that's more accurate than the original data. So we need to round to being as accurate as the original data. So we're going to take this and take it to our least accurate data, which is right here, and go to 2 sig figs. So we had to round up. Excuse me. If we're doing addition, we actually do the number of decimal places. So here we have 1 decimal place, and here we have 1, 2, 3 decimal places. We don't look at sig figs of the whole number, we look at decimal places. So when we actually do this math, we have 1, 2, 3, 4 decimal places. Well, our data is only accurate to 1 decimal place, so our answer can only be as accurate as 1 decimal place. So we're going to round, and here we get to 1 decimal place. So multiplication and division is based on the total number of sig figs of our smallest data point, small. Okay, so for multiplication and division, we're going to look at our data and find the data that has the least number of sig figs in the whole number. And that's going to be the number of sig figs we use in the answer. For addition and subtraction, we look at our data and we find the least number, the data with the fewest decimal places in the data, and that's what we're going to use in our answer. If we have both multiplication, division, subtraction, addition, like if we have a combination, then we go with the number of sig figs. Sig figs trumps decimal places. So remember that dimensional analysis is using our units to figure out our units for our answer. And we will actually have some calculations this year where we do all of the calculations for the numbers, and then we do the calculation for the unit separately. It works easier. And just a reminder that whatever is up here, we want to put down here to cancel out. So this is our 240.0 centimeters is our original value. It looks like we're converting to feet. So here we have a known ratio, and here we have a known ratio. And we're always going to put what we want to cancel out on the bottom. So centimeters divided by centimeters cancels out. And then inches divided by inches cancels out. And so our final unit here would be foot or feet. All right, let's start applying this to some problems. What we're going to do is I'm going to talk about the problem briefly. Then you're going to pause your video, figure out the problem yourself, try it, don't give up, and then come back and we'll talk through the answer and then move to the next problem. So here we have a density problem. We have a 55-gallon drum that weighs 75 pounds when empty. What will the total mass be when filled with ethanol? We have the density of the ethanol. We have our gallon to liter conversion, our pounds to grams conversion, and a little reminder there. All right, give it a try, guys. All right, for a very simple problem. So the first thing is that we need to get that 55-gallon drum into a volume that relates with the density of the ethanol. So 55 gallons, we've got 1 gallon equals 3.78 liters, and 1 liter equals 1,000 milliliters. And just for the sake of demonstration, 1 milliliter equals 1 centimeter cubed. So here we can see gallon. I'll use a different color pencil. Gallon is going to cancel gallon, liter is going to cancel liters, milliliter is going to cancel milliliters, and we're going to end up in centimeters squared. And so the volume of our, what's that thing called, drum, is going to be 207,900 centimeters cubed. Then our next step was to find out, since now we have the volume, what would be the mass of the ethanol when it fills that volume. So mass of ethanol, we have 207,900 centimeter cubed volume, and the density is 1 centimeter cubed equals 0.789 grams. So that's going to give us the mass of our ethanol, which is 164,033 grams. We're not going to do sig figs yet, right? We do that at the end. Okay, now it asks for the total mass, which is, attention to detail there, we don't want to give just the mass of the ethanol. We need to include the mass of the drum also. Now they said that was 75 pounds, and 1 pound equals 454 grams. So that mass is 340,954 grams. We are going to add this number and this number, and we get our total mass of 504,987 grams. Now I'm going to look back at my sig figs. I see that we have 3 sig figs, and we are going to base it on sig figs instead of decimal points because we use multiplication and division. So we want to take it to 3 sig figs. So that means that this guy's going to round this, and our answer is 505,000 grams. We could also write this in scientific notation, which would be 5.05. We still need 3 sig figs, so we would include all those numbers, times 10 to the 1, 2, 3, 4, 5. And it is a positive number because we would want this to get bigger, not smaller, in grams. So this guy here is an okay answer. This is a good answer. This is the best answer. Let's take a look at our next problem. Just so you know, that was a baby chem level problem there. That was not an AP Chem level. Remember, this is review. So if right now you're going, oh, if this is AP Chem, I've got it. Remember, this is the foundation. All right, here we have some density problems. I want you to take a look at these, try them, and then come back for the answers with me. Remember, proper units and sig figs. All right, guys, so here's the answers to those density problems on the last slide. Let's talk about a couple little things here. I'm going to guess that you could do the math just fine, but let's take a look at our sig figs and a couple different ways to look at things. So for our first problem here, we do need to get this down to 1 right there, sig fig. So we end up with this answer when we just throw it into the calculator. And we can either directly take it to scientific notation, where we bring that decimal back behind the 2, and we do a -2 there to show our place value. Or you could convert this to grams. Some people prefer grams to kilograms. And you get 22.59. And then when we go to sig figs, we've got to round to 1 sig fig. So we know this guy's going to round this to 3. So 23 is closer to 20. So 1 sig fig. We would not keep it at 23. That would be 2 sig figs. This guy I think is pretty self-explanatory, except that we have 2 sig figs as our smallest number of sig figs in our data. So that means that we need to round this number to 2 sig figs. And this guy, we get to 1907. We need to get it to 1 significant figure right there. Even though we've got 4 over here, we need 1 sig fig in our answer. So we've got 1907. When we take that to our scientific notation right there, we get 1.9, and we're going to use that guy to round. So we get 2 times 10 to the 3rd is going to be our best answer there. Next problem, vocabulary. Go for it. Okay, so here we go. Remember, intensive means that the amount you have present doesn't matter, and extensive means that it does matter. So there we have intensive and extensive. Then for chemical and physical, really the thing is to think that, can I reverse this process and end up with what I originally had? So baking soda and vinegar, you put that together, you cannot reverse that and go back to having baking soda and vinegar. Once that reaction happens, your baking soda and vinegar are gone. A car rusting, ooh, wish I could reverse that one, right? We cannot. Salt melting on a driveway. Sure, you can reverse that. You can separate the salt and the water, right? And get the water back to ice and the salt back to salt. Milk souring, oh, that would be nice too if we could reverse milk souring, right? Save a lot of milk in my life. Sugar and coffee, we can separate that sugar and coffee back out. And a log burning in the fire, once we burn something, it is burnt. We cannot get it back. All right, quick conversion problems and a little prefixes. Go for it. Okay, so we had 3 problems here to look at. We had bumblebee flying. We needed to convert seconds to hours. Ooh, I want to change my color here. We want to convert seconds to hours, and then we needed to convert meters to kilometers, because that's what they're asking our conversion to be, right? And our sig figs is 2. So we are going to keep, we can have, for here, we could put a 0 here to have 2 sig figs to make it 2 more accurate, or we can take it to scientific notation. I have 9.0 times 10 to the -1. For our second problem, we're looking at the lung capacity of a whale, and we have 5,000 liters. We need to convert that to gallons. And in our original problem, we have 2 sig figs. So even though we end up with 4 here, we take it down to 2 and use our scientific notation. And then our last one was the Statue of Liberty. We're converting that from feet to meters. And then again, we use our scientific notation. I do want to point out that I am writing my units out throughout the problem. You should be doing this to show your work. This is good lab procedure also, because it helps you find where you've made mistakes, and it is a second level of fact checking. It also shows other people your thought process. So you should be writing out the units in every problem. I know in Chem 1, we don't make necessarily that big a deal about it. In honors chemistry, we make a bigger deal about it. In AP Chem, it is a must. So you need to be doing that. Now's not the time for shortcuts. I use the times there. It is fine to still write out your problems with the grid method if you want. I will do that periodically. So this is problem 1 rewritten. You can use this format if that works better for you. That's fine, but you still want to get those units in there, because we're going to have some big problems where you're going to want those units there. All right, and then we had a little prefix vocabulary. This wasn't just to see how well you can look back on a backslide and conjure up information. It was to show you the connections between a positive exponent and a negative exponent. So for like milli, like in millimeter, that's 1,000th, and so it's 10 to the negative 3, whereas a kilo is 1,000, and that's 10 to the 3. So just making a point about that positive and negative, and making those connections to, is it 1,000th or is it 1,000? We've got the same example here with mega and micro, so milli to kilo, and then mega to micro, with 10 to the 6, which equals 1 million, or a micro is 1 millionth, and that's 10 to the negative 6. And then these guys down here I included because we use them a lot. So a nano is 10 to the negative 9. You'll actually see that a lot in biology also because of the size of bacteria and viruses. Centi is 1/10, and a pico is 1/12. All right, some math. Go to it. Make sure you do your sig figs. That's the whole point. So let's take a look here. Not only did we need to see whether we were looking for decimal places or sig figs, but we were also taking a look at our units. So first off, we see we're adding, so our unit stays in inches. And when we're adding, we need to look at decimal places. So our smallest number of decimal places is right here with 2. And so therefore we have 2 decimal places. All right, our next problem, we are multiplying centimeters to grams per centimeter cubed. So that means that these guys are canceling out. And so our units will only be in grams. This is a density equals mass over volume problem, right? We've got our volume and we've got our density, and we're figuring out the mass. We've got multiplication, so we're going to look at sig figs. Our smallest number of sig figs is both here and here with 3 sig figs, which means we need to have 3 sig figs in our answer. Here we've got another density problem. We're dividing mass by volume, right? Centimeter times centimeter times centimeter is volume. So our unit should be grams per centimeter cubed. And we are multiplying, so we are going to look at our least number of sig figs, which is 3 all throughout here. So we have 3 sig figs, and we took it to scientific notation. All right, this guy, pretty easy, right? How many sig figs in each? We do not count the scientific notation in our sig figs. So right here are our sig figs, and we've got 3 and we've got 1. Pretty easy, right? All right, use exponential notation to express this guy with 1 sig fig. All right, we've got 3 point, and we're going to move that decimal 1, 2, 3, 4, 5, 6, 7. So 3 times 10 to the 7. And we're making it, it's a big number, so we're going to keep that positive. 2 sig figs, we've got 3.7 times 10 to the 7. 3 sig figs, 3.71 times 10 to the 7. And 6 figs, 3.7113 times 10 to the 7. So the point of doing this was to show you that we do not actually change the exponent in our scientific notation, even though we're adding sig figs, and that our exponent in scientific notation does not count as part of the sig fig. So that's the point of this whole practice right here. Scientific notation does not count as part of the sig figs. It can help you get to your significant figures in your rounding, but it's not actually part of it. All right, let's do a little bit harder type of problem. So this is an AP Chem type practice. Now it is just density, so it's not too complex, but just kind of to give you a vibe of how we ask problems in AP Chem. So in baby chem, we would say things like, here's the mass, here's the volume, what's the density, right? So let's take a look at an AP Chem type problem. If a 12.3 gram block of an unknown metal is immersed, put in water, totally submerged in water in a graduated cylinder, and the water level rises the same amount as when a 17.4 gram block of aluminum is placed in water, what is the density of the unknown metal? And what is the identity of the metal? You may use the internet to look up known density. So I'm going to give you a moment to do that and then come back and we'll talk about how I solved it. All right, so this is how I solved it. I looked up the density of aluminum, which is 2.7 grams per centimeter cubed. And I figured out the volume of aluminum when there is 17.4 grams, because they said that our volume of the aluminum equaled the volume of our unknown. So I need to figure out what the volume of that aluminum is. So they told us our aluminum block weighed 17.4 grams. We are going to use the density that we looked up to figure out how much volume that aluminum takes up. So this is the volume of the aluminum, and we know the volume of the aluminum equals the volume of the unknown. So now we can figure out the density of the unknown by taking the mass of our unknown that they told us in the problem and dividing that by the volume of our unknown. So we get the density of our unknown to be 1.91 grams per centimeters cubed. I went back to the internet and I looked up densities of metals because they told us that it was a metal, and I found cesium at 1.93 grams per centimeter cubed. So then to do a little additional analysis, it didn't ask for this, but we can figure out our percent accuracy, right, by taking our experimental data and divide it by our known data, and we get 99% accuracy. Or we can take the difference between the two, right, which is 0.02, and divide it by what we would have liked to have gotten, and we got a 1% error. Not bad. That's good data. So percent accuracy and percent error. Just adding some extra stuff in there, right? That's from Chem 1 also. So that gives you an idea, taking that simple density formula and applying it with a little bit more critical thinking skills. Honestly, I find it more interesting you know, easy problems are boring, right? It's more fun to use our problem solving skills and go, how do I solve this? Then here's a formula, here's some numbers, jam them together, right? So we're going to try and avoid that plug and chug mentality as much as possible in AP chemistry. All right. Just a couple more problems here. Let's take a look at another one. You should know right now that I love coffee. And so here we have a large tanker truck filled with 1,745 gallons of coffee. All right. The tanker, oh no, springs a leak and starts dripping coffee at a rate of 204.84 milliliters per second. Devastating. If the truck is traveling 65.4 miles an hour, not too speedy, that's good. How many miles will the truck traveled? Will the truck traveled? That's not good grammar. Travel before all the coffee has sadly drained out of the tanker. All right, go to it. Okay, guys. So this one is a little more plug and chuggy, but it's more about the conversions and knowing to do multiple steps for those conversions. And sometimes you need to do a conversion, do a calculation, and then do a conversion. So I think this one is relatively self-explanatory. Make sure you're writing out your units while you write your formulas, and that you look at those sig figs at the end. All right, here we go. Definitely an AP Chem type of situation, you know, with basic information, but this is the kind of thing that you'll see in labs. You need to separate two granular materials from one another. One has a density of 3.62 and the other one is 2.04. How will you separate the two? And be specific. I'm giving specific numbers. Don't give a generalized answer. All right, see you back here in a minute. Okay, so the generalized answer is that we're going to separate these two guys out by putting them in a liquid with a density that is in between 2.04 and 3.62. If we do that, the 2.04 guy is going to float, and the 3.62 particulate matter is going to sink, and they will separate out. And then we can use filtration, right, to separate those guys. So that's the general answer. The specific answer is to actually look up what could you put these guys into. And the answer is bromine. Bromine has a density of 3.120. Make sure when you're using charts of known data that you check those units, right? Some of these guys would not have it. Some of those known charts would not have the data in grams per centimeters cubed. So that is important. So we will put these, this granular material into some bromine and they would separate out. Our last problem of Unit 1. Water has a density of 0.997, 25 degrees Celsius. Ice has a density of 0.917 at negative 10 degrees Celsius. If a 1.5 liter soft drink bottle is filled, completely filled with water and put into a negative 10 degrees Celsius freezer, at what point should you remove the bottle from the freezer? Go to it. All right, guys, so there's actually a lot more here than meets the eye. So the first thing that we need to do is figure out the mass of the water that is being put in, because we see here that liquid water and ice water have a different density. We're not changing the amount of the water that we're freezing. The amount is the same. What's changing is the volume. So we need to find out the amount that we're putting in there. So a 1.5 liter bottle is the same as 1,500 milliliters, which is the same as 1,500 centimeters cubed. So we're going to take we know that we have 1,500 milliliters of water in there, excuse me, which is the same as 1,500 centimeters. And then we're going to take our density of liquid water, which is 0.997 grams per centimeters cubed, and we get that we have 1,495.5 grams of liquid water. So we're going to take that water and we are going to freeze it. So now we want to find out the volume of when we freeze it. So now we're going to take the density of the frozen water, and we see that the volume of the frozen water is 1,630 centimeters. Well, we know that our bottle can only hold 1,500 centimeters. This is our bottle right here. And so we need to pull the bottle out of the freezer before we get to this amount, because the bottle is going to explode. So we take 1,630 and we subtract 1,500, and that is 130 milliliters. So we need to stop this bottle from freezing when there is 130 milliliters of liquid left. That will be to the size of the container. We should actually probably stop it a little before then, right? So we are looking, when we do the math, that means we're going to stop it when it is 9% or 10% on the safe side is still a liquid, or it's only 91% frozen. So you can see we had a lot of problem solving there and thinking back and forth. All right, that is Baby Boot Camp Part 1, also Unit 1 of Brown LeMay.